These equations are for active mode. Okay. So IC is IS exponent VB by VT minus 1. So that's my collector current. Now, if you want to take early effect into account, then you add a 1 plus VC by V. If you are neglecting early effect, then this term is not there. Okay. IB is this first part that you see here divided by beta F. Because IB doesn't get affected by the early effect here. Okay, so IB is this particular part here. And if we combine them together, we get IC is beta F times IB 1 plus VC by VA. Now, if you look at this equation and you look at this model, what this model is doing is neglecting this particular part here. 1 plus VC by VA. It's simply writing IC is beta F times IB here. Okay, so if you want to be more accurate, this term has to be there. This particular model is neglecting it here. Okay, so that's the model in forward active mode. And as I said, the diode can be approximated by a 0.7 volt battery. Okay, so that's in forward active mode. And this is in the saturation mode, where again the diode is as usual, 0.7 volt battery. The collector based junction, remember we said, is forward bias, and the collector emitter voltage can be approximated by a saturation voltage 0.2. Again, just like I showed you earlier, that 0.7 volts is not really true. For different transistors, you may have 0.6 or 0.8, 0.75. These things vary depending on the current, depending on how the transistor is made. Similarly, this also varies. It may be 0.3, it may be 0.4, it may be 0.1. It depends on the transistor, how it is biased, how it is made. Okay. Now, for the sake of discussion, for carrying out analysis, we take it as a 0.2, but don't, as I said, don't let it settle in your memory that everywhere I see a transistor, I should put 0.2. If you're doing a design, it's best to go and check the data sheet of a transistor from the manufacturer. And from there, you can figure out what this appropriate value is. Okay. So for the sake of discussion in this course, we are taking as 0.2 and 0.7. But otherwise, if you want to be more accurate, look at the data sheets. They will give you, the manufacturer will give you what the appropriate values are. Okay. So that's for the NPN. Okay. NPN transistor. So this is the, all that we have discussed. When we go to circuits, this is the page to keep in mind. The rest was all operation and how the holes move and electrons move and how they recombine and all of that. That's the background. Eventually, when you solve circuit, you require this page here plus a model of transistor, which is the small signal model, which we will do in the next lecture. Okay. So the small signal model and this particular model here. These are the two important things here. Similarly, for the PNP, is exactly the same, except to keep in mind that the diode direction, keep in mind here the current here. So it's not base emitter, which is 0.7, it is emitter base. It is not collector emitter, which is 0.2, it is emitter collector. And the other thing is, of course, the directions of the current that you see. Okay, so that's PNP transistor. All right, with that background, let's take up the circuits now. Okay, so that's the first very simple circuit. So we have a transistor, bipolar transistor. We have 1K resistor here, biased with a power supply of 5 volt. And what is given to us is beta is 100. Beta is 100 is given to us. Other things are not given. So when other things are not given, you will assume that the diode drop is 0.7. Okay. Sometimes what may happen is this drop may be given to you, that as VBE is 0.75 or 0.65. Then obviously you take that value. If nothing is given, then you assume it to be 0.7. Similarly, if VCE SAT or VEC SAT is given to you as 0.3, then take it obviously as 0.3. But if nothing is given, the default values are 0.2. Okay. So this is the circuit that we have. And the goal is to find the collector current and let's say the collector emitter voltage. These are the two things that I'm interested in. Why we are interested in this, we'll see later on when we make an amplifier. Okay. So what we do is, so it's a simple circuit. What we do is we take the transistor out and we substitute the model of the transistor. But then the issue is which model? Is it in active mode or is it in saturation or is it cut off? You remember the transistor can operate in 4 different modes: forward active, reverse active, cut off and saturation region. Can it be in cut off? Can it be in cut off? Look at the circuit here. Can the transistor be in cut off? Cut off means what? No current. No current is flowing into the transistor here. Obviously, I've connected a current source of 10 microamperes, so it's flowing in. So it can't be cut off. It's not possible for it to be in cutoff state. So we just rule it out. Okay. The other one is, so we know it's not in cutoff. Now the possibilities are forward active, reverse active, saturation. Now if you look at this supply here, 5 volt here, and then you look at it, what is the direction that you will see of the collector current? What direction will collector current flow? Flow in, right? Look at this way the circuit is constructed. Current will start from here and flow in. So direction, if you look at the collector current is going in. Can it be reverse active? Reverse active, what happens? The emitter, this acts as a emitter and this acts as a collector. When something acts as an emitter, current comes out of it. Okay, look at this emitter here, right? Current comes out of it. So if this in reverse active, what we are saying is my collector is emitter. If that were true, the current should flow up, which is not possible. Okay, looking at the circuit. So then we are left with two possibilities, forward active or saturation region. And I cannot simply tell, is it forward active or saturation region? So the way we do it is, we assume one. Okay, so typically we'll say the following here. So my arguments are as follows. So we have ruled out two modes of operation. So we are saying it's either forward active or saturation. And then these are, of course, the four modes of operation here. So what we do is, when I'm not sure whether it's forward active or saturation, I say, well, let me assume it to be forward active. Okay, assume it to be forward active. We carry out our analysis, and then at the end we check for consistency. Are our results consistent with our assumption or not? If it is self-consistent, then we say our assumption was correct. If we end up in contradiction, then we say our assumption was wrong. Okay, so that's the method here. So let's apply it here. So for active mode, remember, the transistor, the accurate model is this, but we are going to substitute a simplified model here. So what I'm going to do is, this was my circuit. I will take my transistor out, and instead of the transistor, substitute this model here. Okay, so that's what we do here. We took it out. Keep in mind where the base is, where the emitter is, where the collector is. Take it out, take the transistor out, and substitute the model here. Okay, so we get this model. Now, of course, it's a simplified model. You have a battery here, you have a current source you can easily calculate. So let's do that. We see here base current then, IB is 10 microamperes. So collector current then turns out to be beta F times IB, 1 milliampere here. Okay, and then once we know the current here, we can calculate what the collector voltage is. VCE will be equal to 5 volt minus the drop here, which is minus ICRC, so it gives us 4 volt. So our goal was to find out collector current and collector emitter voltage here. We have found out both these quantities here. But the analysis is not complete. Why? Because it was based on an assumption that is forward active. Now I have to check whether it's forward active or not. How do I do that? Now remember, go back and look at this. How do I check whether something is forward active or not? Go back in NP. If it is forward active, then the drop from collector to emitter will be larger than 0.2. That's the test. So there are two tests of saturation mode. One is that the collector emitter voltage here that you see will be larger than 0.2. Will be 0.5, 0.6, 0.7 or whatever. That's one test. And the other test is IC is less than beta times IB. That's the other test for saturation region. Okay, IC is less than beta times IB. So keep that in mind. These are the two tests here. So obviously, I've assumed IC is equal to beta IB, so I cannot use that as a test, right? That IC is less than beta IB. So what I'm doing is, we check, we have got VC equal to 4 volt, it's much larger than 0.2. So what we are saying is, the transistor is, remember this model here, so we are saying the transistor is in forward active mode. It is in forward active mode, and therefore our assumption was correct, and these are the correct values for collector current and collector emitter voltage. So if you're left with two choices for mode of operation, you have to assume one, carry out the analysis, and then check which one is true. Okay. All right. So let's take up another example here. I think it's very similar. Find IC and VCE here. So we do as usual, represent the transistor in this particular manner. I think there's almost no difference here. RC is equal to 1K, IB 21.5 microamperes, IC 2.15, VCE 2.85. Fine is forward active mode, everything is okay. Okay, so that's a trivial example here. Let's look at this one. It's the same circuit, go back and look at the same circuit, except instead of 1K, what we have done, put 3K. Everything else is the similar as the last circuit here. So, all right. So, okay, last circuit was different from the first circuit in the sense, in the first one we had a current source, and in this one we have a voltage and a resistor here. So obviously we can take this particular loop here, and IB can be very easily calculated. And once you know IB, then you know IC here, and once you know IC, then you know the drop here, and that's how we are. So let's do it for this case. As usual, we assume it to be in forward active. So we substitute a model. We go through our IB, IC, VCE. Note the value. Minus 1.45. So obviously something is wrong. Okay, something is wrong, which tells us that our assumption that the transistor is in forward active mode is obviously wrong. If it were in forward active mode, as we saw, VCE would have come out to be larger than saturation voltage here. So this is clearly telling us that our assumption is wrong. If it is wrong, we have no other possibility except that the transistor is in saturation region. So now we have to redo the analysis here. Okay. Now in saturation mode, remember this is the model that we have. So what we do is, again coming back to the circuit, we take this transistor out, we substitute now this model. Now note one thing here, we substitute this model, IC is not equal to IB, beta times IB now. It is in saturation, okay. So again now we calculate our base voltage here, base current here, we do this. We can calculate base current through this one loop here, and collector current now I can calculate through simply this part here. 5, this voltage is 0.2, 5 minus 0.2 divided by 3K, it gives us 1.6 milliamperes. Collector current is calculated from here, and base current as usual we have calculated earlier, 21.5. If I take the ratio IC by beta times IB, look, it turns out to be 0.744. So it's clearly telling us that indeed my transistor is in saturation region here. Okay. So this is the simplified model that we substitute to calculate the circuit characteristics if the transistor happens to be in saturation region here. 0.7 volt as a diode drop here, and VC drop of 0.2 here. Okay. And when you check you should check and see whether this is indeed true or not. Okay. Now, earlier what I did was I assumed it to be in forward active, found that it was not in forward active, then applied the saturation. It has to be in saturation, and it turns out to be. What we could have done is the other way around also. I could have assumed it to be in saturation region, right? I could have assumed it to be in saturation region, calculate IC, calculate IB. How would I check whether the transistor, my assumption is correct? I will check IC by beta IB. Suppose my assumption were not correct, you would have found IC by beta IB is greater than 1. Okay, then you know, well, my assumption of transistor in saturation region is incorrect. It must be in forward active mode. So I can start with forward active mode and check whether it's true or not, or I can start with saturation, check whether it's true or not. Either way I can start, okay? Alright, this is a slightly different example, similar, except that we've added a resistor in the emitter also. So as usual, you know, you can see here that after you know the model of the transistor, it's a simple linear circuit, circuits that you've already solved before here. So all that we do is we take out this transistor here and we substitute the model. We assume it to be in forward active mode. Now, of course, it's a little bit more involved. To calculate collector current, I need the value of base current here. So what I do is I do this loop. I write KVL here in this particular part here, because note IC will depend on IB here. So I have to start with my base loop here. Okay. So I start here, I write it down, minus VBB, IB and all that. You assume 0.7, and then this drop. Remember, in emitter current is emitter current IERE. So I end up with this equation. Now I've assumed it to be in forward active. What is the relationship between IE and IB? IC is equal to beta IB. So IE will be equal to beta plus 1 IB. Okay, so beta plus 1 IB. So we go ahead and substitute beta plus 1 IB here. Then we have a simple equation in IB, and we calculate what IB is, 14.29 microamperes here. Okay. Now, many times you may simply approximate it as beta times IB also, because beta is 100, doesn't really matter whether it's 100 or 101. Okay. So we have this loop. Next, what we do is we know the base current. We know the collector current then. IC is beta times IB here. So we know this current here. Then we write down this particular side here. emitter current also I know. So I write down KVL in this loop here, and we start from minus VCC, IC, RC, and all of that. And from there, we know IC, we know IE here, and therefore one can write down what is VCE here. So I have that, and we check VCE is larger than 0.2, so I'm fine. So I have the values of IC as well as VCE that I wanted here. Okay. All right. This is something that we just calculated. Now, what you see here is what we have done is we have applied some voltage on the base side through a resistor. We have applied some voltage through the collector side here. And the whole idea of all of these things are to put my transistor in a particular state at a particular point. Okay. And we call this as a bias point or the quiescent point. So the transistor, remember, can be put anywhere. This shows the, along the y-axis I have collector current. Along x-axis I have collector emitter voltage. Okay. And then these characteristics are for different values of base current. So if I have a transistor using these resistors that you see here and bias, I can put my transistor anywhere. I can have my transistor operate here. I can have it operate here, wherever I want. Okay. So this operating point is what we call as the bias point or the quiescent point, Q point or the bias point here. So what I'm showing here is this bias point that we just calculated, IC and VCE, IB, IC and VCE. If I want to show it, it is over here. Because the base current is 14.29, so it lies along this curve. All these curves are for constant base current. Okay, so it lies along this particular curve. So I know so what I do is, given a base current, I go ahead and identify which curve it lies on. And then I know VCE 2.1, so I find a point 2.19, and that's the place where my transistor is operating right now. Now, if I change my, let's say, RC, what will happen to the operating point? Simply, I change RC. Where will it go? I don't change anything else. Where will my operating point, where will my transistor go? Where will it shift? I increase RC. Now, remember, if I increase RC, start looking at this picture here. If I change RC, will it change my base current? Base current is determined by this loop here. Okay, remember, it's this loop. So it's not going to change my base current. Base current is going to remain the same. Okay, because go back and look at the equation that we derived for base current here. Look at this base current here. IB is VBB minus 0.7 RB plus 1 plus beta RE. There is no collector resistance anywhere here. Okay, so base current is decided by your input circuit here. Is decided by your input circuit here. So base current is going to be the same. So it's going to lie on this curve here. Now, as I increase my RC, what will happen? The drop will increase, and therefore my point will shift to the left. Will shift to the left, right? Now, we will see later on when we do bipolar amplifier that my gain of, this is actually, I can make an amplifier using a circuit like this. My gain may depend on RC. You will see. So, the higher the RC that you put, in general, the larger the gain will become, the voltage gain. So, what you would be tempted to do is increase RC to 2K. And what will happen is this will move here. Right? This point will move here. Then you will be tempted, well, let me increase the gain even further. Let me put it 3K. What will happen? It will move here. Right? Now, where are you? Right at this point, if it shifts, where are you? You are at the boundary. Right? You are at the edge of saturation region. You are at the edge of saturation region. Now you increase RC a little bit more, and what happens is it goes here. Once it goes into saturation region, what happens? What is the characteristics of saturation region that you've seen here? The collector emitter voltage is almost a constant. If it is a constant, now, if you're making an amplifier and you're taking a voltage gain at this particular point, it means you cannot get a gain, which means that this voltage does not respond. We'll see very quickly now that in the saturation region, your transistor cannot amplify. It's only in the active mode that the transistor can amplify. So what happens is, you can see here, what I'm trying to tell you is RC for 1K, it is here. So you're tempted to increase gain. So it comes here 2K. Then you go 3K, it comes here. Then you go a little bit here. And then suddenly what do you see? Instead of gain going up, gain just drops. From 150 or 200, gain drops to 1 or 0.5. right? And why does it happen? Because your transistor has gone from active mode to saturation mode. Okay, so graphs like these help us to visualize what is happening to my operating point. Okay, all right. So let's look at this one here. This, if I take this particular circuit and I solve it, I get IB to 21.5, IC is 1.6, VC is 0.2. This is where my transistor is, right here. So it's in saturation region. Remember, I had said earlier that saturation really begins at, if I draw a 0.7. I mean, if I just talk that the base collector junction becomes forward bias, that would happen when VCE becomes less than 0.7. But the real effects of saturation start coming here, when you start seeing changes here. All right, for a change, let's look at the PNP circuit. All right, so we have base, emitter, and collector here. And note that I've used a negative power supply here. We have to cause current to flow from emitter to collector here in PNP. So again, same thing. So, as usual, we assume forward active or reverse active, forward or saturation region. So now I substitute this model, which is nothing but here. It's between emitter and base is 0.7 and current flows from emitter to collector. So these are the changes. So I substitute this model here. Note the direction here. This is -5, 200, and then it goes here. Emitter is at a higher potential compared to the base, 0.7 here, and between emitter and collector, I have current here beta times I. So this is the model that I substitute. After that is a regular circuit. You just do a KVL here in the base loop here between base and emitter, and you get a value of base current here, and then you do a KVL here, same thing here on this side, and you get a value of VEC. So here you don't look at VCE, you look at VEC, and VEC is much larger than 0.2, so you know your transistor is in forward active mode. Okay, so same thing for PNP also, except that keep the the direction of the battery and the current sources in mind, what these directions are. Okay. All right, concept of a load line we have already seen that one of the ways of solving a circuit is for example a diode circuit is you write down the diode equation here, which is given over here, and you write down the equation that comes from KVL. You express it as I in terms of again the diode voltage IV0, so you get two lines here, and then you get a solution here. That's one of the ways of solving it. One can do a load line for a transistor also. Okay. So I can do the following. Note this. What is this current here? Which current? Collector current, right? And this voltage, collector emitter voltage. So you're given a characteristics, right? So one characteristic is the transistor. And in the load line, you derive another collector current versus collector emitter voltage, which is given by the circuit. Okay, so look at that here. Suppose I take this loop here, KVL, I can write minus VCC plus ICRC plus VC IERE equal to 0. Okay, that's the loop from here to here, starting from this to back here. IC is equal to beta by beta plus 1 IE, approximately IE. Many times we take it as this in forward active mode. Okay. Then this equation that you see here, I can rewrite it as VCC by RC plus RE minus VCE RC plus RE. This equation that you see here. So I've already assumed that IE equal to IC. And then I'm writing an expression for IC. Okay. And so we substitute the value we are given RC, RE. So we substitute and we get this. So note, why am I doing it? Because I've got another expression for collector current as a function of collector emitter voltage. Right? Where is this equation coming from? It's coming from the rest of the circuitry. And another IC versus VC is, where is it? Here. This is IC and this is VC. So I have two curves. One coming from the transistor itself and the other one coming from the rest of the circuit. The rest of the circuit also imposes a constraint on IC and VC. So that is this one here. Now this equation, if I plot it, what will it look like? Here. This equation will look like this, a linear line here. Right? So it will look like this linear line. It is intersecting my transistor curves at many places. It's intersecting here. I can draw a curve here also. It's intersecting at many places. What is the operating point? Who decides the operating point? Is the IB. IB decides. So where? So I go here, 14.29. So this is where my operating point is. Okay, so first I have to calculate IB. IB decides which curve I am on. Then I have the transistor characteristics. I have another equation which I call it as the load line here. Load line because it's related to my RC here. RC, typically we may use a load resistor at this particular point, so we call it a load line here. So that tells us where my operating point of the circuit is. Okay. What is this for? Higher RC, everybody sees. If I increase RC, what happens to the load line? Note this equation here. IC equal to VCC by RC plus RE minus VC by RC plus RE here. So if you replot it for a different value of RC, you find this is what the load line becomes. Okay. My operating point goes here. If I make a smaller RC, my operating point goes here. So that's what I was telling you. As you change RC, what happens to the operating point? How it moves to the left. As you increase RC, it moves to the right. As you decrease RC. Alright, so similar things, except that we've already said it is here. So earlier we were changing RC. Now if I change my RB, what will happen now? It will move here. Because what will happen to the load line now? Load line remains the same. Load line remains the same. This line that you see here remains the same. As I change my RB, what do? I go to a different base current range here. So as I change my RB, it may go here, higher RB or lower VBB. Because base current is lower, it means the RB is higher or this voltage is lower. Either one of them. Okay. And similarly, I can go here. So what you're seeing here is that if I fix my input side of the circuit, then I can move along a particular IB curve by changing the value of RC. Or I can move between different IB curves by changing RB and VBB. So these are the things that are under your control. What it is illustrating is you can, by using RB, VBB, RC, put your transistor wherever you like. You can put it here, you can put it here, you can put it very close to saturation, you can put it far away from saturation. All of these things you can do simply by changing RB, VBB and RC. You can put it wherever you like, okay, using this mixture. And that's called biasing. That we are using these resistors that you see here and voltages to bias the transistor at a particular point. Whether it's here or here or here, okay. Alright, so this is something that we've already seen. Okay, let's look at amplification then. Okay, how does a bipolar transistor amplify here? This curve is important. Let's absorb why I get a characteristic like this here. Let's understand. So I have a circuit like this that you see here. All this VBB, RB, and all that are used to bias the transistor. I have RC, VCC here. Okay, the circuit that we have been discussing. And what I have plotted is the following. I have plotted V out. So along y-axis I have V out. And along x-axis what do I have? VBB. This voltage here. Okay. So it's something like output versus input characteristics. This is output and this is the input here, VBB here. And this is the curve that I have. This is cutoff state. Can you keep in mind the voltage here is VBB here. Now, if I obviously apply 0 volt VBB here, if it is 0 volt, what happens to the base current? Remember, what is there between base and emitter? Between here and here, what do I have? A diode. It requires at least 0.7 volt to turn it on. So if I apply a voltage of 0 volt here, what will happen? The diode is off. If diode is off, what is the current flowing into the base? 0. If 0 base current flows, what is the current flowing into the collector? Beta times IB. IB is 0. Collector current is also 0. So if collector current is 0, what is the value of output voltage? 5 volts. So that's why you see it here. If I apply 0, note that this is 5 volt. When do you think it will, the base current will begin to flow? When I apply about 0.7 or so. So you note here, when I apply 0.7, then you begin to see changes here. Right? Now I'm turning my transistor on. So here, in all this region that you see here, till this particular point, my transistor is in cutoff. Very low current. Now, I've applied at least 0.7 volt here. I'm turning my transistor on. As I turn my transistor on, a base current will flow. And as the base current flows, what happens? A collector current flows. And as the collector current flows, what happens to Vout? Because there's a drop now in RC. So the collector voltage, this voltage that you see here, starts dropping. Starts dropping here. Collector voltage is dropping. Okay. Initially from 5 volt, it will drop to 4 and 3 and 2 and all that is dropping here. Now, this point is emitter is ground. What is happening to collector emitter voltage? Is steadily decreasing. So this region, what do I call this region here? Active mode. Why? Because VCE is larger than 0.2. Eventually what happens is you keep on increasing this voltage here. The collector emitter voltage becomes about 0.2 or so. And what happens? The transistor goes into saturation region. Okay? Transistor goes into saturation. And remember what the characteristics of saturation is. The voltage is almost constant. You can see here. Very small and constant. Almost constant. There's a little change here, but this is here. So this is what you find, that as I change my VBB here, this is what happens to my transistor here. To my circuit here. The circuit, the transistor is in cutoff, goes to active and saturation region here. Okay? Can you see an application for this circuit? Not amplification, something else. It acts as an inverter. Right? It acts as an inverter. A digital inverter. Because if I apply a 0 volt here, what do I get at the output? 5. If I apply 5 volt at the input, what do I get at the output? Almost 0.2 or 0.1. So it's a digital inverter already. Okay? Digital inverter is already working as an inverter. High, you apply, you get a low. You apply low, you get a high. So it's one of the simplest digital inverters that you can make. Okay? Now, let's see, amplification is a little bit more involved here. So it's the same characteristics. And now my interest is as follows. I want to use this particular circuit as an amplifier. Right? So what I'm going to do is, I'm going to take this out, VBB out, and I'm going to apply a voltage here. And ask whether my circuit can amplify. What do I mean by amplify? So I'm going to take this out, let's say, and apply a sinusoidal voltage. If it is going to amplify, let's say the sinusoidal voltage is 5 millivolt. If it's going to amplify, I expect a sinusoidal voltage here. Right? That's what amplification means. That whatever signal I apply here, the same signal appears at the output, but in a magnified form. So if I apply 5 millivolt sinusoid here, I expect, let's say, maybe at least 10 millivolt sinusoid here or 50 millivolts or whatever. Right? Greater than 5 millivolt. Then I will say I have amplification. Okay? So that's what I'm going to do. So I took this out. If I take my VBB out, before I apply, when Vin equal to 0, where am I operating? Where is my transistor? Say Vin is 0. Okay, that's the signal that you want to amplify. Where is your transistor? Right? Do you all see that it is at this point? Because if Vin equal to 0, this is where I am. Right? At this point. My operating point is this here. Now, I apply a Vin. And what is this Vin? A sinusoid. So what does this Vin do? Can you see it's a sinusoid here? I apply here. It's a sinusoid, so it will increase a little bit here, then decrease a little bit here, like this here. What will happen to the output voltage? Remember this graph. Look at this graph. It is V out here and V in here. So what will happen to V out? Remember this voltage is small. We are talking about 5 millivolt. Okay? What will happen to the output? Will anything happen at the output? 5 millivolt, you go a little bit here, it's still 5 volt here. And you go a little bit here, it's still 5 volt here. Nothing happens at the output here. It remains 5 volt. Does it amplify? No, actually no sinusoidal signal appears at the output at all. I don't get any sinusoidal signal. Okay? So this is what I end up with here. I get 5 volt. So if I look at it, I'm applying a sinusoid here that you see. V in 5 millivolt, and at the output all that I'm getting is 5 volt. Nothing. No signal. Okay? It doesn't amplify. What does it tell you? my transistor in cutoff state will never amplify. Okay, that's what it is. Okay, now let's take here. Let's suppose now, so it's not going to amplify. That's why you see I need to bias. I need to add some voltage. Then only it will amplify. So I've added 1.1. 1.1 takes me here, operating point. Okay, it takes me here. Now on top of that, so this 1.1 is not the signal that I want to amplify. It's just for biasing. So I've brought my circuit into this particular state. Now on top of that, I add my Vin. I add my Vin. On top of that, in addition to 1.1, I add Vin. So it is here. Now what will happen? Your output is going to respond, right? If it'll note that if Vin, it will go here. So it's going to respond like this. Right? You'll get something at the output here. So when you don't apply any input voltage here, 1.1, you are getting this value here, whatever 2.7 or whatever it is. Now when you apply a sinusoid, the net voltage increases a little bit and then decreases a little bit. And as a result, output voltage increases and decreases. Okay. Now you get a signal here. The sinusoidal signal that you applied here, it has propagated to the output. You get a signal here. Now, when do you think I will get a amplification? If the slope of this particular line is greater than 1, what will happen? Just think about it. Slope of this line is greater than 1. Then any change along x-axis will cause a larger change along y-axis. dy by dx is greater than 1. So all that you require is that this slope is larger than 1. And then what happens is any voltage that you apply here will appear in an amplified form. Okay. Now you see amplification. You see that the signal that you've applied here, it appears here in an amplified form. Okay. So that's what we have here. Note that I applied 5 millivolt again. And at the output, what do I see? At the output, I see, you can see that there's a DC, right? There's a DC part. And go back here and see that there is a DC part here. And on top of DC, there is this AC which is riding, right? So that's what you find here. When you don't apply any input voltage here, then of course you get a DC here, and the DC is 2.745. And in addition to that, now we have a sinusoid. And what is the amplitude of the sinusoid? So what I do is, if you want only the pure signal, then what you do is, after this, maybe put a capacitor. If you put a capacitor, the capacitor will take out your 2.745. It will remove the DC, and after the capacitor, you'll get the pure AC. So that's what you can see here. So this is my input here, the red one, 5 millivolt, and this is my output here, the black one there. And you can clearly see that I get amplification. Okay. So where do you get amplification? You're getting amplification if you are in the active mode. In cutoff, you didn't get. In active mode, you are getting saturation region. I mean, you're getting amplification. And let's next put it in saturation region here. So here, let's put it in saturation. Let's take my transistor and put it here in the saturation region. Okay. And again, apply a voltage here. Sinusoid. What do I get at the output? Nothing. As you apply the voltage higher or lower, nothing really changes here. So you don't get amplification at all. So it tells you which place you get amplification. You are not going to get it in cutoff. You're not going to get it in saturation region. You'll get it in active mode. Now, of course, I'm sure you're wanting to know how much is the slope. What determines the slope? Okay, those are the things that we'll see in subsequent courses. But what this is illustrating is that that if you bias it in active mode, you can get the amplification, and cutoff and saturation will not give you amplification. Now, it's also telling you the following. Let me go back here to this picture here. It's telling you that this is where I bias here. This is the bias point, operating point. Now, when I apply my signal, what happens to my transistor? Transistor goes a little bit down and then goes a little bit up here. So it's moving along that axis, right? Because the net voltage that you see here is 1.1 plus 5 millivolt. Okay, so it's moving down and it's moving up, right? So now you increase this value here, the voltage here. Now what it will do? It will move even further up and further down, right? Now you increase it even more. What happens to this point? It will move all the way here and then all the way here. You increase it even more. What will you find? you will find the voltage is constant. It's no longer responding. You're increasing the input voltage here and your transistor now goes here. It no longer responds. The voltage is constant. See, amplification means if I increase the input, the output should increase. If I decrease it, it should decrease. So you're realizing that as I increase my input voltage here, eventually my transistor is going like this, increasing here, more and more here. Eventually what will happen is it will reach this edge. Once it reaches this edge, it no longer responds to input voltage. And you will begin to see distortion. Your sinusoid will start getting clipped at 5 volt. And once it reaches this, again it will get clipped. So you'll begin to see that there are limits to how large a voltage I can apply. After that, it will not work here. You're also seeing from here that maybe there is a good operating point and there's a bad operating point. For example, suppose I had taken my operating point, I had not used 1.1. Okay, suppose I had used 2 volt here, 2 volt here. Where would I have been? 2 volt, I would have been somewhere here, right? I would have been somewhere here. Now, how large do you think I can apply Vn if I'm here? How large can I apply Vn? Not very large. I will quickly go into saturation region here, right? So it's a bad operating point. Similarly, I could have used a very small VBB. I could have been here. It would amplify, but very quickly it will go into cutoff state. So again, it's a bad operating point. So you are seeing the consequences. Where do I put my operating point? What value of 1.1 do I choose? Should I choose here? Should I choose here? All these things are important. Now, interestingly, how do I move it? So one way of moving, operating point here and here is by VBB. The other way of changing is also RC. We'll see later on that the slope of this graph, in fact, you can do it through your own calculation and show that the slope of this graph depends on RC. RC will decide the slope. Go back and see here. This one here. So we said the moment you increase this voltage here, the transistor goes into active mode and you have a certain current IB. What is the collector voltage here? VCC minus ICRC, right? VCC minus ICRC, right? That's V out. What is the del V out by del V in? What will it be? VCC is constant. Del IC by del V in multiplied by RC. So you're saying the slope depends on RC here. The slope of this particular line depends on what RC I choose. So you may, again, as I said, you may be tempted to use a RC which is high. And therefore, to get a larger gain. Because the slope is dependent on RC. But then as you change RC, what happens is operating point also change. So those are the complications that enter. And so we'll see how to bias and where to bias and all that here. Okay. So all right. Okay. So one of the things is you can't simply take a transistor, apply a signal at the base and assume it to be amplified. It will not amplify. You have to bias it from the base side at a suitable point and then apply an input and then it will amplify here. To determine amplification factor, how much is the amplification? We need to carry out small signal analysis. Can you see the need for small signal analysis? If I don't apply this V in, I have VBB and VCC and all of that. They take my circuit, put it at some place, some operating point. Now, what am I doing? I'm adding an incremental voltage here. And this incremental voltage, what does it do? It causes incremental changes in currents and voltages everywhere, including an incremental change in base current and incremental change in collector voltage here. And that incremental change is nothing but in response to this increment here. And that's nothing but amplification that we are looking for. What is the change in this voltage in response to this voltage here? That's the amplification. And because this incremental voltage is small, we do small signal analysis here. Okay, because the transistor inherently you're seeing here base emitter voltage is an exponential diode. So that is a nonlinear characteristics. And when we apply a small voltage, then we can linearize it and use small signal model here. So small signal models are needed to understand what the amplification factor is. Okay. So let me stop here and